Hey everyone, welcome back. In this lesson, we're going to go through just a few more graphing examples, but the second way that we've been doing them. So sort of going backwards. So we'll draw a few graphs and we'll figure out the equations that go along with those graphs. And what we're going to do in this lesson is we're going to just go over a few sort of a couple of special cases. So first, we're going to go through an example that involves a negative slope, just for a little bit more practice. And then just to show you how to sort of go about it, we'll also do one horizontal line and one vertical line. So there's a little bit of a spoiler there. You kind of know what the graphs are going to look like, but I think it'll be good to see just at least once what happens if you're trying to find the equation of a horizontal line or a vertical line. So we'll do an example of each, and we'll study how it makes sense. So we'll go we'll go at a decent speed for the first one, because we have done a couple of examples now of finding the equation for a negative slope, and it's really, you can see it's the same process as finding the equation for a line with a positive slope. So we're getting more familiar with the process, so we'll go at a decent speed for that, and then we'll just look at those two examples, one for a horizontal line, one for a vertical line, and that'll basically be it for this video. So I'm not quite sure how that's going to pan out. It might be a little shorter, might be a little bit longer than the half-hour mark, but we're going to target something around 30 minutes. So just in general, because we're doing a few examples of finding the equation, we'll just call this one a few more examples. Just some useful examples in general. It gives you an opportunity to see a couple of the special cases that we've talked about. So basically horizontal lines and vertical lines, and we'll talk about why the equations for those ones make sense. So what we'll do is we'll start off as we always do. We'll draw our axes here, our x and y axes of the Cartesian plane. Whoops, that doesn't look particularly straight. Actually, maybe it's all right. Maybe it's all right. Now it's definitely not great, but yeah, whatever. I'll redo that. So the axes will never change that in this unit or in the next unit. I'm thinking we'll still do quadratics as our next unit. You guys might remember doing quadratics last year. But we're going to spend a unit on quadratics this year as well. We'll sort of go over some of the same things that we talked about last year, but maybe we won't go into too much detail in that, and then we'll see how much time we got left going into the end of the school year to do some trig. So some good old-fashioned trigonometry that we covered last year as well. So let's continue with what we got going on right now. Draw in your axes and put in a few tick marks, maybe up to about 4 should be enough. If you happen to squeeze in a fifth one, that's fine. But the questions that I've drawn out for today involve going up as high as 4 tick marks and no more than that. So if you have 4, you should be good. If you have any less, you might end up just going off the graph a little bit for one of the questions, but don't worry about it too much. That looks decently spaced. I think we'll make do. Before I number them, I'm going to put in some of these dotted lines so that I don't forget to do that after. We'll just have some of those going in every 2 squares, just so that we can kind of work out where we are when we're drawing in the big empty white spaces. Like that. Does that look reasonably straight? It looks reasonably straight. I think it'll do given let's just kind of miss the line. Ooh, let's try that again. Something like this. Okay, that's a bit better. Of course, when I'm drawing these in without a ruler, they're not going to be perfect. But as long as they're good enough to get the job done, that last one is absolutely not good enough to get the job done. But in general, if they work well as sort of like a guideline, that's all you really need. You don't need them to be much better than just to give you a rough idea of where your dots are supposed to go. Maybe I should start on this side, go for the horizontal ones. Yeah, so it gets a little bit wonky sometimes. It could get a little bit of a wavy line going, but as long as it serves its purpose of helping us locate our points, that's all we can really ask for. I think that looks decently straight as well. Yeah, these are a little bit wavy. I'm going to blame that on my hand being tired from writing a midterm this morning. The midterm was not necessarily that much work per se, but I'm going to use that as my reasoning nonetheless. But yeah, so once you've got this drawn out, hopefully yours is going a little bit quicker than mine. Once you've got this drawn out, we'll start with our first function. If you guys happen to be sitting around at any point during this lesson without anything to do, so like right now, draw out 2 more of these because we're doing 3 examples in this video. I'm going to just erase the line and use the same grid so I don't have to keep redrawing it. So if you want to save yourself some time and draw out a couple more, you can go ahead and do that right now while I finish this up. But that's only if you're done. Otherwise, we'll go together. There we are. That is a -4 down here, just so that we're clear. 1, 2, 3, 4, and those are all positive ones up there. I know the 2 looks like we got a -2 going on, but that's a +2. Okay, great. So once you've got this drawn out, we're going to plot the following 2 points. For the first one, we're only going to plot 2 points, and honestly, we could. I don't know if that's big enough. I'll make that a little bit larger. I also wrote plot instead of points to plot. Yeah, we're only going to plot 2 points for the first one, and just to really drive home the point in the next 2, in the horizontal and vertical lines, just to drive home the point, no pun intended, we will plot 3. So the 2 points that we're going to plot in this one, let's label them right off the bat because we know we're going to use that 0.1, 0.2 thing. So I don't know if that looks like a P or a D, so let's redo that. 0.1 is going to be at 0, 2. So 0 in the x direction, 2 in the y direction, and point number 2 is going to be 4, 0. So in this one, we've got a little bit of an unusual situation where I've given you 2 points that both have zeros, but I mean, I guess that makes them a little bit easier to locate. So these are the points that we're going to plot, and let's go ahead and do exactly that so that we at least have our line on there, and then we can erase some stuff and work on finding the equation. So 0, 2, the first point here, P1. So 0, 2, the 0 is telling us that from the origin, we don't have to move left or right. We don't have to move anywhere in the x direction. So we don't have to worry about that 0 at all. And we just focus on that 2, which is telling us we have to go up 2 units in the y direction. So we start at 0, we go up 2 units, and we put our point right there. All right, we should hopefully be getting pretty good at figuring out where the points go. It's everything else that I understand if it still takes some time, like finding the slope and putting it all together in the equation. I get that that takes time and practice, but hopefully we're getting more used to actually plotting the points. It's just instructions from, if you start at 0, the first number is just telling you how many steps you have to go to the right or to the left only if it's negative, and then the second number, the one after the comma, is telling you how many steps you need to go up or down only if it's negative. But yeah, you could think of it as like directions, like on like a GPS or something. If it's telling you go 0 steps to the right and 2 steps up, you know, on like a map or like in a video game, then you could figure out how to get from point A to point B, right? Or point 1 to point 2 in this case. So hopefully the plotting of the points isn't too much of a struggle, but let's go and plot the second one. So we've got an x value of 4 here, and a y value of 0. So the y value of 0 is telling us we don't need to move up or down, but the x value of 4 is telling us that we need to move 4 units to the right. And it's to the right because it's a positive number, so we start at 0, and we move 1, 2, 3, 4 units to the right, and because we have a 0 for the y-coordinate, we don't have to move up or down, so our point sits on the x-axis. And so once we've got that, we can plot, or we can draw our line going right through this. So I'm going to try to do exactly that. So we've got our line looking something like that. All right, hopefully your line looks somewhat similar to that. As you can see, it has a negative slope because it's tilted downward. Remember, our lines with a positive slope look like that. So this time it's a little bit different. We got it going this way. So we can tell that the slope is negative. Now, I think I can get rid of this bit on the points to plot, so let's do that. But what I will do is, just to help us find the slope and stuff, I will rewrite the points up at the top, and I'll get rid of the title now, because we know we're doing a few examples. So let me put the points up here. So we have point 1 is 0, 2, and point 2 is 4, 0. All right, fantastic. Now, let's remind ourselves of the equation of a line. Always start with that equation. So if you're lost, write this down, and then hopefully you'll see somewhere where you can go from there. So let's start off with the easy bit. We know that we need to find two pieces of information. The first one is the slope. The second one is the y-intercept. Now, if you happen to be given a point where the x-coordinate is 0, which we have been in this question, then the y-intercept is the easiest thing to find. So you might as well get that done and out of the way at the beginning. So because we have a point where the x-coordinate is 0, having an x-coordinate of 0 tells us that we're sitting somewhere on the y-axis. So whatever the y value for that point is going to be your y-intercept, because if you have the point sitting on the y-axis and you have a y-coordinate that's been given to you for that point, then that's telling you where this line crosses the y-axis, and that's the definition of the y-intercept. That's what it means. That's what the y-intercept is. It's where does your line cross the y-axis. So if you've got a point where your x-coordinate is 0, then the y-coordinate of that point is your y-intercept. So in this case, because we have the point 0, 2, we know that our y-intercept is going to be that 2 sitting right there, which we could also obtain from looking at the graph. So that tells us we can throw that 2 in right here, that our y-intercept is equal to 2. And I'm thinking right now, I haven't written up your test, and we're not necessarily going to have the test for a little while because I'm debating on whether I want to do something a little extra. To sort of add on to the end of this unit, but I think I'll try to be nice on the test, and any graphing questions where I just give you the graph and I ask for the equation, I will give you a point that sits on the y-axis so that you can find the y-intercept without too much of an issue. I might make a bonus question where I don't do that, but don't stress too much about a problem like this. Is that my laptop making noise? I guess it has to be my laptop making noise. Alright, hopefully it calms down soon. Alright, so now all we need to do is we need to figure out the slope. So what we're going to do is we could do rise over run, and we could do the x2 minus x1 kind of deal as well. So what I'll do is maybe we'll do it both ways. Let's do it both ways. So I'm just going to throw the y-intercept b equals 2 up over there, and then I'm going to erase this because I kind of need the space if I'm going to do it both ways. So we know our y-intercept is equal to 2, but we want to find our slope now. So we've got two ways to do it. So our first way is rise over run. So we've got rise over run. Now let's look from our first point, P1, to get to our point P2. What is our change in the y direction? What's our rise? Now remember, if we were going up, if we were going in that direction, that would give us a positive value. But because the positive y direction is up, and going from the first point to the second point, we need to fall, we need to move down, that's telling us that we're going to have a negative rise. So we know it's going to be negative something, right? This line is our fraction line, and that's my minus sign. So how many steps do we have to go down to get from this point until we're in line with that point? So we can see that that point's on the x-axis. So we want to know how far do I have to fall from this first point to be on the x-axis so that I'm in line with that second point. And the answer to that is 2. You fall once, you fall a second time, boom, you're on the x-axis. So that's telling us that our rise is -2. And then we can find our run by asking ourselves, okay, once we've gone down 2 spots, we're basically sitting back at the origin. Now how many spots do I have to go over in order to reach the actual point itself? And the answer to that, of course, is 4. So we move over 1, 2, 3, 4 units like that, and boom, we land at point number 2. So we started here, then we fell 2 spots, so that's our rise of -2, and then our run is +4. Positive because we're still going in the positive x direction. So then we've got that our slope is -2 over 4. But if you remember from our fractions unit, we can actually simplify this, and we know that -2 over 4, -2 over 4 is equal to -1 over 2. That's basically you're dividing out 2 from each of these, top and bottom. So you end up with 1/2, and that minus sign stays there. So then that's telling us that we get a slope of 1/2. So I'm going to write that up there, but we're going to solve it the other way as well, just so that you can see that it still works. Even the reducing and everything still works. So if we do it the other way, we get slope is equal to, and then we write out our formula, so that's going to be y2 minus y1 over x2 minus x1. And hopefully you guys are getting more comfortable with this process as well. But if we plug those numbers in, then we get that our y2, so that's the y-coordinate of point number 2, so that's a 0. So for our y2, we're going to have 0 minus, and then y1, that's the y-coordinate of our first point, so that's 2. So we've got 0 minus 2 in the numerator, and then in the denominator we've got x2, so the x-coordinate of the second point, which is 4, minus the x-coordinate of the first point, which is 0. So if we go ahead and do the subtraction, top and bottom, we're going to get that our slope is equal to, on the top we've got 0 minus 2, that's -2, over, and then on the bottom we've got 4 minus 0 is still 4. That gives us the exact same -2 over 4 that we had before, which we then reduced to 1 over 2, or -1/2, right down here. So that that way hopefully you can see that the slope is indeed -1/2 no matter which way you try to solve it. So there we go. Now over there in that corner we've got, these are the 2 crucial pieces of information that we were looking for, and now we have enough information to put it all together in the equation. So if I get rid of what we just did over here, I'll get rid of just this top part because hopefully you guys will have that written down by now. I'll just get rid of that. Then if we remind ourselves of the equation of a line, we know the equation of a line is y equals mx plus b. We know m is equal to -1/2, so we'll just sub that in. So instead of m, I'm going to write -1/2. The x is going to stay. And then in place of plus b, I'm going to put that 2. Now, since it's a positive 2, I'm going to leave the plus sign there. If my b was a negative value, I just put a negative sign right here. So I'm still going to leave the plus sign here because our y-intercept was positive, and our y-intercept happens to be 2, so we put a 2 over there. And that is the equation of the line on the right. And now, hopefully you can see, so from our, just one thing I wanted to point out, our slope, we reduced this from -2 over 4 to -1 over 2. Now, -1 over 2 as a slope is telling us that we have a rise of -1 and a run of +2. Now, if we do that, let's see what happens. So if we start at our first point, and then we take a rise of just -1, because that's what our slope is apparently telling us. If we take a rise of -1, that brings us down to just here, right? Just this point right here. And then we have to go over 2 units instead of 4, right? That's 2 units from down here. So we go down 1, and then over 2, And would you look at that, it still ends up on the line. It gives us actually a new point that we didn't graph, but you could use the exact same method, and you could use this slope instead of the -2/4, and it would still give you a point that lands on the line. It's just not one of the points that we started with. So that's totally valid. If I gave you a slope of something that you could reduce, so if I gave you a slope of something like 6/8, and you wanted to reduce that to 3/4, go right ahead. You can reduce that to 3/4 and then do your plotting with 3/4 instead. So I might give you a question where when you calculate the slope, you get something like 2/4, which I'm asking you, if you want, you can reduce that to a slope of 1/2, or you could leave it as 2/4. I don't really care, as long as your graph looks correct. That's the important part. Okay, hopefully this particular problem makes sense. That took way longer than I thought it would, but let's get through, let's look at a second one now. So draw your second Cartesian plane. I'm going to work on erasing the graph of the line for the first one and just keeping the rest of the grid kind of intact. So let's see if we can actually do that. Get rid of all of the information that we don't need, and then we'll get rid of the actual line. So I think I might have to do this with my finger. Okay, so let's get rid of these. Maybe I should have, thinking about it now, maybe I should have done the arrows in a different color, because I've started taking out 3 markers. Earlier on in the school year, I used to just take out the 1 marker and sort of hope that that was all I ever needed. Now I've started taking out 3 markers, and then I still end up only using 1. So my apologies for that. Yeah, maybe I can use this. Alrighty, and then we'll just redraw in what I erased, and hopefully your construction of your Cartesian plane doesn't take too much time. But there we go, something like that. Okay, so let's get cracking with the next point. So we're gonna, with the next graph. So points to plot this time. Okay, so we're going to plot 3 points now. We're actually not going to, if you want, you can call them point 1, point 2, point 3, but we're not going to use the equations that we've been using thus far to calculate the slope and the y-intercept, and I think you'll see why in a second. So we're going to plot the points 0, 3, 2, 3, and 3, 3. So these are the points that we're going to plot. So if we begin with plotting that first one, hopefully you've got your graph drawn out by now and we can start drawing it. If not, let's get through that as quickly as we can. So we'll start with plotting 0, 3. Now 0, 3, 0 is our movement in the x direction, right? So that's telling us we don't need to move left or right, we only need to move up 3 units, right? We only need to move up 3 units. So from our origin, we start down here, and we move up 1, 2, 3 units and plot a point right there at 0, 3. Perfect, not too much trouble so far. Next point is 2, 3. So it's still 3 in the y direction, but now we're moving over 2 units in the x direction first. So we start with that 2. So we start from our origin, we go over 1, 2 in the x direction, and then we go up 3 units in the y direction. We go 1, 2, 3, and that puts us right about there. And now we got one more. I know I'm going a little bit fast, but hopefully this isn't too much work to keep up. Now we've got 3 in the x direction and 3 in the y direction. So we start off from the origin, we'll go 3 in the x direction, 3 in the y direction. 3 in the positive x direction, so to the right, and 3 in the positive y direction, so up. So starting from our origin, we go 1, 2, 3, and then from here we go up 1, 2, 3. And that puts us right about there. Now you'll see that these dots aren't necessarily evenly spaced, but what you will hopefully notice is that they are all at a y value of 3. Right? That was hopefully quite evident from these points right here. You can see the y value is 3 for all of them. So now let's think about the equation of our line. So first we're gonna deduce what the equation is, and then we're gonna talk about why it makes sense that it is the way it is. So first things first, our y-intercept. We know, I'm gonna go through this a little bit quickly because we just talked about this. We know that if you have a point where your x-coordinate is 0, your y-coordinate of that point is just your y-intercept, right? Because the 0 is telling us that we're not leaving the y-axis, so we're not deviating left or right from the y-axis. So that means that this second number, whatever it is just telling us where on the y-axis we sit, and that is your y-intercept. So this is telling us, this 0, 3 is telling us that our y-intercept is 3 in this particular problem. Now, here's the thing. Our slope, what is our slope for a horizontal line? Now, we talked about this a little bit before, but in case you've forgotten, our slope is always 0 for a horizontal line. So that's just a rule. And we know we have a horizontal line because the y value doesn't change, right? The y value not changing tells you that it's basically flat. If you were trying to, like, if you had like a big Cartesian plane that you built your house inside, you'd want your floor to be all at the same level. So that, you know, things don't roll around and stuff. Maybe some of you guys are crazy and you want your floors to be all tilted so that you can, I don't know, roll bowling balls around the house. But you, most of the time, you'd probably want your floor to be pretty flat. So if you had like this giant Cartesian plane just, you know, sitting out in the middle of the town and you went to go build a house there, you'd want to make sure that all of the points in your floor are at the same level so that it stays flat. And so basically you want your floor to have a slope of 0. So in this case, with this line, we've got a slope of 0 because all of the points are at the same elevation. They're all at the same y coordinate. So what that's telling us is if we've got a slope of 0, if we plug that into this equation, that's telling us that our equation for this line is y equals 0x plus 3. But the thing is, 0 times x is just 0. 0 times anything is going to be 0. So what this is telling us is that we could just kind of forget about that whole 0x right there, and we could just say that this equation is y equals 3, where that 3 came from our y-intercept. Remember that our b value is 3, and so that's where that 3 came from, but that's the only thing that survives. The m and the x both disappear because of the slope being 0. So what we're left with is an equation that says y equals 3. Now, why does this make sense? If you think about it, this equation doesn't have any x's in it, right? So basically, when we were drawing out the little you know, function machine thing from before, when we were drawing out that little function machine guy from before this thing, you put in an x value on the left side, and it's going to spit out a y value on the right side. Now here's the thing, the equation in the middle, the equation is the thing we would write in the middle, so we would have like y equals x plus 2. So you put in an x value, it would add 2 to it, and it would spit out that y value. But the equation that we've got in the middle this time is y equals 3. It doesn't care what value you put in for x, it's always spitting out a big old 3 on that side because of the equation in the middle. It doesn't care what you put in for x. You could put in 5, you could put in 50, you could put in 371.2, you could put in pi times Euler's number, you could put in infinity. You're going to get 3 as your y value because it doesn't care what your input value is. You could put in 0 for x, you could put in 1,000, you could put in negative 1,000, it'll still spit out 3 on that side, and we can see that on our graph. Regardless of what our x value is, so regardless of how far away we go to the right or to the left, the y value is always 3. So this equation down here hopefully makes sense. There is no, we call it x dependence. Y doesn't depend on x. The x doesn't show up in the equation for y because it doesn't care. For this particular equation, y doesn't care what x has to say about it. Y just is 3. The y-coordinate is always 3 for this particular line. So let's extend that idea to a slightly more complicated situation. Not really that much more complicated, but it's only more complicated because of the way we tend to use our y's and our x's, but it's exactly the same logic. So now what we're going to do is we'll draw one more Cartesian plane, and hopefully we can zip through this in a few minutes, because I gotta get to bed. But we are going to do a vertical line now. So I'll tell you in a sec what points I want you to plot, and then we will plot those points, and then we'll come up with an equation, and we'll figure out why the equation makes sense. Okay. I've got a few marks around here that I'm not really that happy with, but I think for the most part we're doing okay. So, points to plot for our third and final example of the night. Points to plot. I guess of the day for you. Points to plot. We're going to plot the points 2, 2, 2, 0, and 2, -1. So we're going to start off by hopefully speeding through the plotting part, because I know you guys know how to do this by now. It's just a matter of whether or not you're done drawing out your Cartesian plane. But I'm going to go ahead and plot those. So we start off with the point 2, 2. So that means we move 2 in the x direction and then 2 in the y direction. So both positive, remember. So we start from the origin, we move in the positive x direction, which is to the right. So we go from 0, we go 2 units over to the right to here. And then we go 2 units up, which is going to bring us right there. In the middle of that, like crosshair. So there we go, there's our first point. Our second one, 2 in the x direction, again, but 0 in the y direction, so we don't need to move up or down. So we start from 0, we go 2 in the positive x direction, so we go over to here, but then we don't need to move up or down, so we just plot our point right there, right on the axis. And then our last point is 2, -1, so that's still telling us 2 in the positive x direction, and then -1 tells us that we're going to be moving down one step, because, well, the second number tells you where you're moving in the vertical direction, and if you have a negative in front of it, it means you're moving down. So we start from our origin, we go over 2 units, and then we go down a unit to right there. Once again, just like the last problem, the lines, the dots aren't evenly spaced, but hopefully you can see that they all lie on this line right here. This vertical line right here in this case. So that's what this particular graph looks like. And here's the problem. How are we supposed to find an equation for this now? Let's figure it out. So if we tried to go about this the old way, you don't have to write this down, but you can if you wish. If we tried to use the equation of a line, thus y equals mx plus b, we've got two problems. One, we don't know where this line intersects the y-axis. We don't know where this line crosses the y-axis. So what do we fill in for b? If the line never crosses the y-axis, and in fact we know it doesn't cross the y-axis because I've already told you it's a perfectly vertical line, and the y-axis is perfectly vertical. If these two are both vertical lines, they're parallel to each other, and parallel lines are never ever going to touch, which means that this line is never going to cross this axis. So we don't have a y-intercept because there is no place where the line crosses the y-axis. So what y-intercept? The other problem is our slope. What's our slope? If we try to calculate it the mathematical way, we get y2 minus y1 over x2 minus x1. Here's the problem. The x values are always 2, right? We plotted 2, 0, we plotted 2, 2, we plotted 2, -1. The x value is always 2, which means on the bottom you're always going to be doing 2 minus 2, which is equal to 0. So I don't care what you have on top. You could do 1,000 minus 1. You could do 1,000,000,000 minus pi. You'd get something on top, nobody cares what it is, over 0. And if you've brought your calculators with you, try punching in, 3 over 0, or 10 over 0, or 5 over 0, or 1 over 0. You should get something like an error, or a math error, or calculation error, something like that. Depending on what type of calculator you have, they'll give you a different type of error because we can't divide by 0. So that's a problem. What this is telling us is our standard equation of a line is broken for a vertical line. We can't use it to figure out a y-intercept, and we can't use it to figure out a slope. Maybe you could, with like a little bit of a hand-wavy argument, you could say the slope is infinity, but what are you supposed to do? We've got y, that would tell us that then, okay, y is equal to infinity times x. That's not really useful. And then we still don't know what to do for plus b. It's not 0, because if it was 0, that means it would cross at the origin. But it doesn't cross at the origin. Does it cross at positive infinity? Does it cross at negative infinity? So do we have like infinity x minus infinity? Like what's going on? It gets really messy. We can't do it that way. We're not going to be able to solve this using a whole bunch of infinities and trying to write out the same equation of a line that we always do. But what we are going to do, we can still get an equation for this line. We just need to think about it more like the last problem than like our standard problems where we use the equation. So we're actually going to take this equation for a linear function and chuck it out the window. And the reason for that is that this is not a function per se. But by that definition, I mean that a function is one where if we take that little function machine, if I put in one x value on this side, so I put in like a 3 or like a 10 on the left side, then when I spit out a y value from the other side, it's going to give me the exact same y value every time. So I put in one x value, it spits out one y value. And that's how we write it out when we're putting those coordinates, is that this is the x value I put in, this is the y value I got out, and that never changes. For this particular question, what happens if I put in a 2? If I put in a 2 on the x side, what y value do I get? I could get -1, I could get 0, I could get +2, I could get +4. I haven't marked a dot there, but like there's totally a dot right here. I could get positive, like, I don't know, 7. Again, it's not on the line, but like you could see that it would be if I kept drawing the line that way. Could be -pi, could be, I don't know, could be Euler's number, E. It could be positive pi. It could be pi over 2, which is like over here. All of those are valid. Every number, in fact, is valid. I could put in negative infinity and it would technically work. I could put in positive infinity and it would work. And I could put anything in between those. I could put 0, I could put 4, I could put 15. Anything I want would come out for y, which means I can't write out 2, comma, and then a single value over here, which is a bit of a problem, right? And the other thing is, if I put in any other number, if I put in, let's say, a 1 instead of a 2, let's look at our graph. At an x value of 1, what's the y value? We don't have a y value that lines up with x equals 1. There is no dot anywhere with a coordinate of x equals 1. And we can't just say that it's 0, because that would tell us that it's 1, 0, and that there's a dot right here. But we don't have that. So we can't write 0, we can't write infinity, we can't write nothing. So there's no way to write this out for any point that isn't exactly the number 2. And when it comes to the number 2, we have an infinite number of possibilities. So we can't write this out the function way that we have been so far. Our function machine is broken for this problem. We've got some smoke here because it's, it's having a bit of a crisis and a poorly drawn fire. Yeah, our function machine is broken. It's not happy with vertical lines. So we have to think about this differently. What do we know? If we look at our graph, we know that the x value is always equal to 2, right? That's what we know. We know our x value is 2 here, our x value is 2 for this point, our x value is 2 for that point, and it's only the y value that's changing. And that actually even though it sounds like I'm going to keep going, that is the equation for this line. X is equal to 2, and that's all the information you need. If your x-coordinate is 2, that point is on the line. X-coordinate is 2, x-coordinate is 2, x-coordinate is 2. As long as your x value is 2, it's going to lie on this line somewhere. And this makes sense the exact same way that the previous one did. In the previous one, y didn't have any x's, right? We had y equals 3. Our equation didn't have any x's because no matter what x we put in, we always got a y value of 3. So that was all we really needed for our equation. In this one, it's a little bit backwards because our function machine itself kind of broke, but it doesn't matter what y value we choose. We know the x value is always positive 2 for this particular graph. And so that's why, well, actually, I didn't mean that as a joke with like x's and y's, but that's why this works as the equation for this particular line. If you've got a vertical line, that means the only thing that's common between all of those points is whatever the x value is, right? That x value is the only thing that's not changing, otherwise it wouldn't be a vertical line. So the only way to describe that line then is x equals 2. All right, now hopefully that makes sense. It's totally understandable if it doesn't make sense, because it's a little bit hard to wrap your head around a concept like this. But if you guys have any questions, as always, let me know down in the comments or send me an email. Thankfully, my schedule for midterm exams has finally started to lighten up. I've definitely got a couple of other things going on, and I have something like 20 things due in the next 3 weeks. And I wish I was exaggerating, but no, I mean 20 like homework assignments or tests or midterms or something in the next 3 weeks. Yeah, so it will be a little bit of a time crunch on a couple of occasions probably to get these videos out, but I will still be getting them out for you. I will still be checking the YouTube account every day or two whenever I go on to post a new lesson, so I will check for your comments then. But yeah, other than that, if there are no questions, I will see you all in the next video. Have a good one.